Unit 9, problem post number 2, dots factoring, difference of two squares factoring. Be sure to fill out your pre-score, number 1 through 5, assessing your ability to factor an expression using the dots factoring technique before watching the video. This video's guest of honor will be a pirate. Okay, to use the dots technique, we want to rewrite this difference of two squares as the product of conjugates, meaning the product of two binomials that are exactly the same except for the sign between the terms. So, to set up a product of conjugates, I'm going to make two groups of parentheses. One's going to have to be a plus, one's going to be a minus. Now it's a matter of finding the square root of each of these terms and placing them in these parentheses. So the first term I have here is x squared. The square root of x squared is x. If I have a variable to an exponent, I want to divide that exponent by 2 to find the square root of the term. And the square root of 36 is 6. So my result, x plus 6, x minus 6. Number 2, we have a very similar problem. We want to set this up as the product of conjugates. One's a plus, one's a minus. I have x squared again, so I already know that the square root of that is x, and the square root of 16 is 4. And remember, we know the square root of 16 is 4 because 4 squared is 16. 4 times 4 is 16. Again, just like with greatest common factor, we could imagine using the distributive property to get our original expression back. X times x would give us the x squared. 4 times negative 4 gives us the minus 16. And usually we would have a middle term here, but if we were to get the 4x and the negative 4x, they'll end up canceling out that middle term. So we're just left with the x squared and the negative 16. Negative 3, we notice we still have perfect squares, 4 and x squared, so I can set up my conjugates. One's a plus, one's a minus. This time the number comes first, so when I write my conjugate binomials, I'm just going to make sure I keep the number first. So the square root of 4 is 2, so I'll have 2 in the first position, and x squared will be an x. In number 4, we can try to use our difference of two squares technique, but we notice that 2 and 18 are not perfect squares like the rest of these problems. But using the greatest common factor technique, we can actually factor out this 2. So I'll first factor out the 2. That will yield x squared minus 9. And now notice the result in the parentheses is the difference of two squares. I can't forget about that 2, so that'll have to come down. And then I'll set up my parentheses for conjugates. One's a plus, one is a minus. Square root of x squared is x. And the square root of 9 is 3. Number 5 presents us with a fraction. If we're trying to use the difference of two squares with a fraction, we just need to make sure that both the numerator and the denominator are perfect squares. In this case they are. 4 and 25 are both perfect squares. So my conjugate pairs, one's a plus, one's a minus. We can put x's for the first position because the square root of x squared is x. And now for the fraction, we're going to do the square root of the numerator divided by the square root of the denominator. So the square root of 4 is 2, and the square root of 25 is 5. So I'll have x plus 2/5 and x minus 2/5. Looking on to the back, we see we have x squared plus 25. Now, the technique is called the difference of two squares. Difference implies subtraction. However, I'm not subtracting here, I'm actually adding. So because I'm adding, this expression doesn't fit the difference of two squares technique. So this is actually not factorable. So I'll just write that, not factorable. So all because of this plus sign. It's not a difference, it's a sum. In number 7, we notice that 5 and 80 are both not perfect squares. Neither are perfect squares. And we have x to the third, which is not a perfect square. But we can factor this using the greatest common factor first, and then maybe we'll be left with some perfect squares. So I notice both of these terms are divisible by 5, and they both have at least x. So I'll factor out 5x. That will leave me with x squared minus 16, because 80 divided by 5 is 16. Factored out an x from x to the third, so 3 minus 1 is 2. That gives me my exponent. I had x, but I factored out x, so no x next to the 16 anymore. X squared is a perfect square, 16 is a perfect square. I have a subtraction, which is a difference, so I can use dots. Can't forget about my 5x though. So I'll bring that down and I'll set up my parentheses for conjugates. One's a plus, one's a minus. Square root of x squared is x, and the square root of 16 is 4. For number 8, we have x to the fourth minus 16. As long as the exponent of a variable is even, we know it will be a perfect square. And we simply need to divide the exponent by 2 to find the square root of that variable expression, variable term. So I will make two groups of parentheses. One is a plus, one is a minus. The square root of x to the fourth is x squared, because 4 divided by 2 is 2. And the square root of 16 is 4. Now, once I factor this by dots, I can actually check both groups of parentheses and notice this one here can be factored further. This is also the difference of two squares. This is a sum, so this one has to stay the same. So I'll carry down the x squared plus 4, but I'm going to split the x squared minus 4 into the product of conjugates again. So I'm applying dots for a second time on the same problem. Two groups of parentheses, one's a plus, one's a minus. The square root of x squared is x, and the square root of 4 is 2. And there we have it, factored completely by dots twice. Be sure to fill out a post score, number 1 through 5, assessing your ability to factor an expression using the dots factoring technique after watching the video.